Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, in the morning, when we started the event, Dennis Gannon mentioned that there are 5 to 10 people who we can identify easily as thought leaders in computing. One of them is Ed Lasovska, one of them is Dan Reed, and one of them is Dave Patterson. And I went to the Wikipedia to find what can I say about David Patterson. You saw a few minutes ago the delegation from Brazil, so enthusiastic that they decided to come and take a photograph. And I was hoping the delegation from Italy, the delegation from Spain, and the Germans would like to do that as well. So who is David Patterson? He is former chair of computer science at Berkeley. He is past chair of the Computer Research Association, CRA. He was a member of PTAC, which is the Presidential Information Technology Advisory Committee. So he advised the President of the United States in technology. And he has written 5 books, one of which he wrote with John Hennessy. And one day I went to his office and I saw the book translated into the Basque language. And, and we went through the pages of the book and we found that even the figures are in Basque, even the comments are in Basque. So I asked him to sign the book, and to keep the purity of the language, he signed the book in Basque. But what we had to do is we have to go to the web, get some phrases in Basque, and he wrote that. So he's a wonderful researcher. We cannot measure his impact by the number of papers or the number of conferences. We have to measure it in terms of awards. He has 30 awards in research, teaching, and service. And he leads 2 laboratories, the RAD Lab and the PAR Lab, and he's starting a new effort, AMP Lab. Probably we're going to talk about it. It's a great honor for me. It's a great pleasure for me to present him. And here it is.
Thank you. Well, it's great to be here and see old friends, and I hope make new friends. I'm going to make sure I have at least 15 minutes for questions at the end. And so I was a little worried that I didn't have enough, so I may have to skip some slides. And the first thing I'm going to talk about is what is cloud computing. And, you know, Juan has a little bit of an accent, so I'm afraid some of you think I'm going to talk about this. But it's cloud, not clod computing. This, for you Brazilians, this is somebody falling down the staircase. That's a clod in English. Okay. Other people think of cloud computing as cloud computing. Larry Ellison, the CEO of the famous CEO, billionaire of Oracle, hates cloud computing. He said, as far as I redefine cloud computing, do everything we already do. All I have to do is change a couple of lines in the ads. And so the cloud computing became extraordinarily popular, and it was hard to understand what everybody meant by it. There were strong claims that were hard to believe. So a group of us at Berkeley, including Armando Fox, who's here in the audience, decided we would write a white paper about it, see from an academic perspective what we thought was important and what wasn't, trying to clarify these terms. And we put the paper out there a little over a month ago. It was a technical report, and thanks to the miracle of the web, there were by a year later, there were 50,000 downloads, making it surely the most popular paper any of us has worked on. And for those of you who are members of the Association for Computing Machinery, the current issue of the Communications of the ACM has a shorter version of that article in it. So why did we think we could offer an interesting perspective? As you'll see, we've got a really strong engagement with industry over the many years at Berkeley. And we've been using it in both our research and in our teaching since 2008. We think it's a really big deal, and we're going to try and highlight what the big things are. So this is the arrival of the long-sought idea of utility computing, as you heard Shirley earlier today, about how little it costs to use it. And it was kind of a breakthrough in low cost with little promises of what it would do. In particular, it's very interesting there's no contract that had to be done and just billing to the nearest hour. That's unlike anything that anybody tried in the past, and is certainly caught on. Software as a service, you could think of the old time-sharing systems going back to the 1960s as software as a service. There's a big mainframe. It runs all the software. You have this cheap terminal, and all the work's done in the thing that's far away from you. In this hype around cloud computing or enthusiasm around cloud computing, all kinds of terms got thrown around, and as we went through them, we couldn't figure out what some of them meant. We couldn't figure out what the difference was, hardware as a service or infrastructure as a service or platform as a service. So we pretty much just talk about cloud computing and software as a service. But what we think is different is this pay-as-you-go utility computing, the illusion of infinite resources on demand. That is a brand new thing in computing. Often, always in the past, if you could get much more scale, that you had to pay more than linear. If you wanted 1,000 times as many computers, you'd have to pay 10,000 times as much for the right to do that. The fine-grained billing, that this is another new thing, that you not only can grow, which computer science has been worried about growth for a long time, but you shrink. Shrinking is new. That never made sense. What do you shrink? Would you burn some of your computers, right? That doesn't make sense. You bought them, you want to use them, and then when you buy more. So shrinking is new. And a bunch of people, this isn't the first attempt to do utility computing over the last decades, besides time sharing. There are other attempts by companies like Sun Microsystems and Intel that got into cloud computing and really didn't make it. So why? So I think our take on it is there's this web space race is where these companies like Google and Microsoft and Amazon were becoming more popular, so they had to build even bigger data centers. And as they built them at the scales of tens of thousands, and they built them out of these commodity components, they recognized they were getting these incredible economies of scale, surprising economies of scale. Who would have thought that if you bought 10,000 PCs, it would be tremendously cheaper than buying 100 PCs? Maybe it's not so surprising that network bandwidth, if you buy gigabits per second, is tremendously cheaper per megabit per second than if you buy a megabit per second. Maybe that one is not so surprising. But they repeatedly found, for all kinds of important costs, that there was economies of scale. If you acquired a very high volume, you get it much cheaper per unit. It's so much cheaper that you could sell it and make a profit. And I think that's why this happened. They were forced to build it, and they recognized what they had, and then people started selling it. If you had these services in these data centers and we didn't have good connectivity, that wouldn't have done them any good, but we do. And this commoditization of hardware and software with the popularity of virtualization that runs pretty fast, standardized stacks, that also helped. But I think primarily it was the web space race that did it. So the data center is this new server that you could think of it as, I'm kind of a computer architect, and you could think of designing a whole building at a time. This is an effort that Microsoft is doing. They have in Chicago, it can handle, I think it's 2,500 containers. We actually have a container at Berkeley next to us that we bought because we ran out of space inside of our building. And this container has as much useful cooling and electricity as almost the whole building. And increasingly, it's not the space, it's the power and cooling that does it. This center that could be 1 million servers that Microsoft has is pretty phenomenal by lots of measures. 300 megawatts, dual water-based. So they're building the biggest computer collections for commercial uses they've ever seen, and they're getting these economies of scale and offering it for us. As we'll see at this conference, there's a whole bunch of different bets are going on. I think of this as the early days of cloud computing. We're trying to see which is going to work. Now, maybe all three of these bets will work. What you heard, you hear about Amazon EC2. That's on the left of the spectrum. That's less managed, lower level. It's at the instruction set, virtual machine architecture. That's what they provide, and it's up to you to manage it and scale it up. At the other end is what Google is offering with the App Engine. They'll talk about that. That's highly managed. They'll do the scaling for you. And Azure is in between. So here are these companies with these different skills, all of whom have been successful in providing big services, and they're thinking this will be the thing that people want. And so I think we're going to find out over the next 5 years whether all of these will succeed or one will dominate. So that's what's kind of fun being in this field, right? Things change fast, and it has huge impact both on people's lives and financially, and we'll see how this all works out. So from our perspective as a cloud computing user, when at least a year ago when Armando and I were working on this, a lot of the arguments were about what's about the cost effectiveness of cloud computing, and so we wanted to add our arguments for it. And we take a lot of the perspective of providing a service. So if you were trying to create a new company, create this thing that you hope to grow, what is it from your perspective? So typically, if you bought the computers yourself, you want to make sure you have enough capacity to meet demand. All of these internet services even companies the size of Microsoft and Google will see differences between night and day, and even on the weekends. There's less work on the weekends. So maybe there's factors of 5 to 10 between the peak and demand. So if you build for the peak demand, a lot of the time that's idle. And of course, with a virtual data center, you can grow and shrink, right? So that's one of the, you have less unused resources as a cloud computing user. So what's the danger here if you're a startup company doing it? Well, one danger is you think you're going to be so popular, you overbuild, you take all your money and you build this gigantic data center, and actually you're not all that popular. So you've sunk all that money into your data center even though you hardly ever use it. So that's one danger. The other danger is the opposite of that. You don't want to waste too much money, so you don't have enough capacity to meet demand. So what's going to happen? So we had two scenarios here. One is you're providing this internet service, and the users, they run in, and then they can't log on anymore, and yet they keep coming back every day. We think a more likely one is you become popular, you run out of your hardware capacity, those people get frustrated by it and decide not to come back, and eventually you stop getting enough users so you actually meet the capacity. But you've lost that revenue, you've lost those customers, and it's not a great thing if you're a company trying to become a popular service. So so that's kind of this internet service perspective. I think we think people use it for two ways. They provide these services, or they do kind of batch processing. They have a lot of computation to do. And what's striking to me is this, what we call cost associativity, that you could get 1,000 CPUs for 1 hour, and that doesn't cost any more than 1 CPU for 1,000 hours. And that's a remarkable statement that's never been true before. So what made, actually, how we got into this is the feedback we got in our research in cloud computing is we were, like a lot of researchers, trying to do cloud computing, and our example was 20 servers in Iraq. And the feedback we got from industry was we understand where you start, but you have to figure out a way to do your research at the scale of 1,000 servers. And so we went back and, geez, what are we going to do? We're going to get 10 more containers, and where are we going to get the money and the power to run that? We agreed with the comment to do cloud computing research. We had to do a larger scale, but there was no way, even if we could get the donations, that we had the manpower to operate that. So then we got interested in cloud computing and tried to find those resources remotely. So with I think it's, Armando can correct me, less than 6 months after the comment, you need to figure out a way to do your research at the scale of 1,000. We went back, thought about it, explored cloud computing opportunities, and I think wrote a paper using 1,000 processors 6 months after that comment. I think that's right, and that was accepted at a conference where we went from like 20 to 1,000, and we couldn't have done it without cloud computing. So that's from a research approach, and then kind of the poster child that Amazon talks about, or used to talk about, was Animoto, the startup company that they'd kind of do a music video for you automatically. You'd supply some pictures and some music, and they'd create a music video for you. Well, somebody finally plugged it into Facebook a few years ago, and for every 12 hours, 3 days, they doubled. So they went from needing 50 servers to 3,500 servers in 3 days. So there's no way you could have planned for that as a startup company. You would have had that resources around. And then not only did they grow up, they could shrink after it became, after things calmed down, they shrink. So they wouldn't have put all those orders for 3,500 servers and have them sit there idle. And then from a business's perspective, often you couldn't do this even if you wanted to. Your IT organization wouldn't allow you to buy a lot of computers. You have to plan years in advance, and they have the space and resources and cooling. So kind of, another way to think of cloud computing, it's like the PC revolution. Used to be there's the mainframes, and they would say what you could do and how much cycles you could get and terminals, and they controlled the computing budget. And the personal computer unleashed that. You could take your money instead and buy a PC and have your own computer and do whatever the hell you want, and they couldn't stop you. Right? That was a big change in the computing industry and people's experiences. Cloud computing has some of that. Right? Cloud computing is, I'm not going to take my money and give it to the central servers. I'm instead going to take my money and go outside of my organization and do whatever I want with it, and you can't stop me. And so that's another kind of mind-expanding opportunity here. And then one of the things we talk about a couple times is you don't have to pick one or the other. You don't have to do all your computation in your computing center and never use cloud computing, or you don't have to burn all your servers and do everything in cloud computing. You don't have to do that. What's we call it surge computing, and I think more popularly it's called hybrid computing, is you have a set of computers, and then when that surge comes, you surge into the cloud. So the cloud provides that insurance like Animoto needed that suddenly became popular. You need hundreds or thousands of more servers, but you could still have your own set there. That'll have some advantages in privacy. What it means, though, is that the software stack that you're using in the cloud, you have to be running locally so that you can seamlessly do that. But I think a lot of people will find this one an interesting compromise. One of the things that I am surprised about is when I talk to my friends in high-performance computing about this, and because this seems pretty obviously important, is they don't get it. There's a couple of technical reasons, but primarily, to the first order, they'll do this calculation. How much does it cost for me to buy a cluster, run it 24/7 by 3 years? How many hours would that cost in some cloud computing provider? And then do the analysis, and then cloud computing is more expensive. We're not going to do it. So what does that ignore? Well, it ignores taking a graduate student who wants to become a Nobel Prize-winning physicist and turn him or her into a system administrator. So, that has an actual dollar cost, and they may not be the very best system administrators, so they could lose a lot of data. And I would feel a little guilty of taking this guy who wants to, or girl who wants to win a Nobel Prize and turn him into a system administrator. The other thing they ignore is the cost of space, power, and cooling, because they don't pay that, right? That's the campus's problem, right? Right now at the Berkeley campus, the financial problem is everybody's problem. Everybody, when the campus has a financial problem, we all have a financial problem. So saving the campus money is a good thing. we should care about that. And then the thing I really don't understand is they don't appreciate the opportunity cost. I mean, we're in this race, especially in science and in chemistry and physics and biology. People are often trying to discover something about the natural world, and the first person to do it gets the glory, right? Doesn't it seem obvious that the time, something that would get you there faster would be valuable? So if instead of 20 servers for a year, you could do 1,000 servers for a week, that's about the same amount of computation. Wouldn't you want to have a 51-week head start over your competition? And when I talk to them, I don't understand why they don't understand the value of that. For those of us who have environmental concerns, the information technology does all kinds of computations, but maybe we use up as much, we have as much a carbon footprint as the aviation industry. I flew up an airplane here right now, and maybe it'll be twice as bad in a few years. So is there anything about cloud computing to save energy? Well, yeah. Basically, a lot of these machines, when you buy machines, they're idle a lot of time. They're sitting there unused, but wasting power. More or less, if you have your computer on and it's doing nothing, that's 2/3 as much power as if it's completely busy. So idle computers are wasting power all over the place. Isn't it a lot better to all combine our resources and ship photons over fiber rather than electrons from dams around here not down to Berkeley? Much more environmentally friendly. And not only that, it allows us to, there's finally an economic incentive to turn things off. When we tried to argue with our friends at these companies, they should turn things off when they aren't using them, and they said, well, there's a lot of practical disadvantages of that. All of our sensors are based on the machines working. You ping the machine, it responds back, it's working. If we turn it off, it won't happen, all our monitoring won't work. So no, we don't want to do it. Well, now there's an economic incentive. Why are you leaving your servers on? You're wasting money. If they're idle, you should turn them off. So the economics match kind of a behavior that you would like as responsible engineers and scientists of trying to worry about the planet some by not wasting power when you're not doing anything. Okay, and in this paper, we said, this is really exciting. We think it's going to change the world, but there's a lot of challenges to go. So these are both technical and non-technical, and we decided to pick a top 10, and I'm going to go over those. The paper has a lot more details and some examples on how to do that. So the first one is what are 5 obstacles to growth? And one of them is, how do you program these things? Well, Armando at 1:30 in that room is going to talk about a really exciting new idea called CJITs for selective embedded just-in-time specialization. And we think it's going to have impact on both cloud computing and on multi-core computing and programming in a really high productive system. You want storage that can grow and shrink, just like computation grow and shrink. You'd like a computer to help you grow wisely, and shrink wisely. That's another challenge. Performance unpredictability. One reason scientists don't want to use cloud computing is the problem of simultaneously scheduling. So that's another challenge for cloud computing people. One of the surprising challenges is the speed of the internet. It's not all that fast if you want to transfer terabytes of data, and surprisingly, FedExing disks is a pretty fast, high bandwidth way of doing it, and there are actually services that provide that. Since we published the paper, the people are actually doing that. How about adoption challenges? From a business perspective, one of the worries is you put your service up there and the company you're using goes away. We can't think of any other way to do that than to provide use multiple organizations, so that you could provide it to more than one place. And a related thing is data lock-in. I put my data up in the cloud. That service goes away. How do I get my data back out? So we think you have to use multiple providers, and for multiple providers to be interesting, there has to be standardization. And so standardization helps with lock-in and things like that. A lot of time, I think if there are often people from industry and there's a cloud computing talk, one of the first questions will be, what about data confidentiality and auditability? We think there's technologies that can be helpful in that. And surprisingly, a lot of companies that you would think, or industries you think would be afraid of cloud computing, like pharmacology or the banking industry, are some of the biggest users of it. It'd be great if every company that provided cloud computing would list all of who their customers are, but right now we don't know what that is, so people think this is a big problem, but lots of those companies are using it. Kind of a more nerdy thing is reputation faith sharing, that if somebody in your cloud does something that gets them banned, that could affect you as well. And then, pay-as-you-go licensing needs to become popular rather than just pay the CD model of it. Okay, so that's a quick cloud computing, what it is. Software as a service in education. This will be more computer science-y. In reflecting, what we've been doing is it's a typical depth-first curriculum where we dive into a particular topic all the way to the bottom is a typically way to do things, where this Web 2.0 approach to programming is more holistic. Lots of things are coming together. One of the things, Armando has led the way in teaching these courses, but one of the things that's really interesting is these modern programming languages or scripting languages, highly predictive languages like Ruby and Python, really take advantage of modern ideas in computer science. They have meta-programming and closures and high order, and not only do they have them, they show how it makes you more productive for programmers. And this happens to be a perfect fit for undergraduate education. You exactly want some kind of tools that are highly productive so you can create an app in a short amount of time, like within a semester or a quarter, and they actually work at the end. And plausibly, the tools can really do that. This is in contrast to what we've done in the past, which, because it's so hard to get the thing working, often at Berkeley at least, it's kind of fill-in-the-blank programming. Here's all this infrastructure. You got to figure out what to put in there, and then you get it to work. It's focusing. These courses are focusing on the software as a service environment rather than, say, on a more traditional platform. And Ruby on Rails is this high-level framework that we've been using, and we expect the projects to work. So the classes Armando and I have taught together, maybe a dozen or 2 dozen projects. We expect a dozen or 2 dozen projects to work at the end of the semester, and I think that's often not the case, ironically, in these courses. I think that just said that. Okay. So that's kind of the software as a service. What about cloud computing with education? Boy, is it a good match. Cloud computing is a good match to education. We only teach, I guess, 30 weeks a year we're teaching, and we don't need computing all that time. We were able to do a thing where we could overload a database so they can get some idea of scalability. Well, we needed 200 servers per student to do that. We could do that. Or 200 student servers for the class. We never could have done that at Berkeley if we'd done it locally. There's not that many servers there. There were in the cloud. The lab deadlines, homework deadlines, and projects, we had this system to coordinate between all the classes to make sure we all didn't do the same homework at the same time, because that would wipe out our little computing infrastructure for instruction. Well, we're trivial compared to a cloud, so we didn't have to worry about that. So it just scaled up when we needed it. And it was cost effective as is, but it was nice that Amazon Web Services even made donations to make it even more cost effective. Virtual machines are a really good idea in dealing with courses. Often you have special software or stuff crashes and things. It made it very easy to create an image and everybody just used it and reloaded it as they needed it. The hardware's modern, right? These cloud computing companies are making investments in hardware, and instructional computing is not often the top priority in a campus, and we can get this cost associativity to scale up. And for Amazon, we can do this eucalyptus thing where we could run it locally and surge into the cloud. So this is just what we did before. Before we ran things locally, and in the cloud we switched over to using cloud versions of all this. And in particular, we really didn't have a system administrator. That's the name of a local system administrator who his health had a lot to do with the success of the class. He had to fix all these problems, and if he wasn't around, everybody in the class suffered. We just didn't have those problems because of the cloud. Success stories. These are actually, the amazing thing about this Ruby on Rails environment is the students cannot know anything, and by the end of the semester built something that looks like this that actually works, as I'll say. So people debate was to get people on both sides both sides of an issue, and you could see the debates on the screens. How about commuting? That's a big thing in the Bay Area. People talking about you was FOUNDIT, I think, and Hesperian was to share health information to the third world countries. These were things that had, they worked, they had pretty good user interfaces, and all happened in a semester, and were all deployed in the cloud. Okay, so comments from students who took the course. They took the more traditional software engineering course in Java. That would have taken us at least twice as long if we'd done that. And typically, if you taught software engineering courses, kind of the ironic thing, you're trying to teach good programming practices, and a lot of time the projects don't work. Right? Doesn't that seem like there's a problem there? But that's different here. That's the same thing here. So what's the difference? Rather than everything installed on laptop, it's up in the cloud. You're doing it for a class project. Well, since it's on the cloud, a lot of the students would start showing their friends when it started to work. So what a remarkable, inspiring service. It's not just an assignment that you do. Some of your friends start using it, like FOUNDIT and things like that. Well, then you start worrying about user interfaces. You start worrying about dependability and issues like that. I can't remember any of my course projects I ever did. They're all dead at the end of the course. Well, these things live on, and in cases like we showed, the app can outlive the course. We had an example, remarkably, of somebody wanted to do a health app in it wasn't Tasmania.
It was somewhere in Africa.
Somewhere in Africa. And they knew somebody in Africa. They're trying to do a health app for boarding school, so they actually had a doctor in the boarding school help them with the design of the app in this undergraduate class, and deployed it there as well. The virtual machine images is a really great way to be able to create what somebody uses, and then the students bragged about this in the resumes. And this is the thing. It wasn't just I took our course and got an A. They would write what they did on their resume, and often the interviewers were, they knew more than the interviewers about a lot of these things from the hands-on experience. So it was a really inspiring experience. So I think the SaaS is a really, the tools for SaaS, and as a target, it's a highly motivated target. In part, you can show off to your parents, you show off to your friends, and you actually get something working in this semester about something you care about and deploy it on the web. And just cloud computing just seems perfect for courses, right? We only need it some of the times of the year. That's when cloud computing is at its strength. All right, I'm on schedule. So what is cloud computing? Boy, it seems like a good match to the education. And what's the RAD Lab research project? So almost 5 years ago, or I think we're 4 years into our 5 years missions, we said we think it'd be an interesting research challenge to allow one person to develop, deploy, operate the next generation internet service. So we'd always use eBay. So eBay was, the first version was created over a long weekend, but then they had to build up this giant corporation with hundreds and thousands of engineers to turn eBay into what it was then to have millions of people use it. Wouldn't it be great if you didn't have to do that? Is if we could invent the technology that one person could come up with the idea, and although they'd have to use cloud computing to get enough computing resources, they could scale it up and operate it themselves. So a handful of people could do that, in this case one. So we brought together people in systems like Armando, Randy Katz, and I. My joke about machine learning is we have the Michael Jordan of machine learning, whose name is Michael Jordan. And people in networking and security, databases all together there, and this is about people. The reason all these logos are here, the Bush administration inspired us to find industrial support for our research project. And their inspiration, Ed Lazowski and I, who do these national things, were simultaneously trying to get DARPA to continue to fund things. And we just got documented evidence today that what we said was true, is they cut academic funding in half. And we said that, and people made fun of us. Well, not people. The people in the Bush administration made fun of us for saying that. And we have, yep, they cut it in half. Well, simultaneously, when we were trying to argue for research funding, how was I going to do my research without funding, right? Well, we better figure out how to work with companies. And fortunately, Microsoft and Google and Sun all stepped in as major donors. And then over the remaining years, we've added many more companies as affiliates to this project. And so it's primarily an industrial-funded research project, which was another thing we tried on this. The fundamental bet, I didn't say that, the fundamental bet was that statistical machine learning would help us reach this goal, is we were going to use computers and modern ideas in machine learning to allow things to be scaled up and to see what was wrong and stuff like that. So how were we going to do that? It wasn't just we're going to get really smart people. We wanted machine learning to step in. Would it work? And it worked, I would say. I mean, I think the good news is that that really worked. I'll give you some examples, but predicting the performance of complex systems, automatically adding and dropping systems to if you're violating what they call a service level objective. And as I'll talk about, one of the amazing things is take millions of lines of source code without telling it what's important, turning it into a one-page decision tree to detect anomalies by somebody who didn't build the system. This is our organizational slide. This Elvis character comes from Microsoft programming personalities. And so there's Einsteins, and there's Morts at the bottom of the food chain, and Elvis is in the middle there. So we wanted to enable Elvises to operate a data center like this. In the lower right is our software stack, which has virtual machines and operating systems, the Ruby on Rails environments. And then we had a trace collection system that's called Chuckwa and Xtrace, and that's at the base there, so we can collect the data together so we can feed that to machine learning. And the Web 2.0 apps. A storage system I'll talk about later, a scalable storage system, it's called SCADS. And then the log analysis, which I mentioned, we're able to take the trace information and do the machine learning log analysis. I'll talk about that next. And then to run this whole thing, we needed something like the operating system for the data center. That operating system supervisor has been used a lot, so we use the term director, and I'll tell you a little bit about that. The idea is this director would inform the operator of what's going on, and the operator would approve of decisions that the director would make, and sometimes just let the director make them on their own. But that was our vision. So let's talk about the console logs. So console logs are these things the programmers write individually. They write a note typically to themselves into the log. Well, now a data center will have, or an application will have programs from hundreds of people. So these logs will have this information operators or the developers wrote, not operators, developers wrote for themselves, have all these intermixed in there. It's millions of lines of code, tens of millions of lines of code. What do people do today? They typically write Perl scripts. The operators, not the developers, will write Perl scripts, look for the log, and try and find something interesting. So not surprisingly, this doesn't work very well. And actually, most of the time, people just ignore what's in the logs. They don't even look at them. So what we wanted to do is use the magic of machine learning to, without telling it what to do, it would find interesting things that'd be useful to the operator. So kind of the problem is 24 million lines long. Add machine learning and give advice to Elvis over there on the right. So that sounds like a hard problem. So what the student who led this did was first he parsed the logs to turn them into something useful. Machine learning works best with numbers. And then after parsing the logs so a computer it was more understandable, he did feature extraction. So what are interesting features that we should feed into machine learning? And he came up with a couple that he thought would be interesting. Then we used more or less standard machine learning algorithms, in this case PCA. And then finally, those machine learning results that said, boy, this looks interesting, is hard for the operators. So he turned it into a decision tree, which is basically if this happens less than that, then it's a problem. If not, go ahead. And then you go down to the bottom of this, and you see there's about 8 red things on the right, and then finally it's okay. But it boils it down to a single page, amazingly enough. And it works extremely well. The student who did this, who's graduating soon, is going to visit other companies in the Bay Area that are web services and trying to use their ideas there, because he's basically said there's this untapped resource that you've been ignoring that'll be very helpful for you to understand when something strange is going on in your system. So it's worked out even better than we hoped. What about this growing and shrinking of the data center? That's this idea of what we call a director, which is the thing that does things, and then we have advisors that are the intelligence behind that. And so our model is that we have a bunch of advisors that are watching parts of the system, have models of how the system works, and that gives input to the director who, using the virtual machines, turns things off and on and scales them up. I think I just said those things. So how about storage? So computation growing and shrinking, we see how that works, but databases don't usually. That databases grow, but they don't particularly shrink. What would that mean? A storage system that could grow and shrink. So we decided that there wasn't something that we could easily use, so we developed our own system called SCADS for Scalable, Consistently Adjustable Data Storage. And the goal is that you could build the small system, and then as your users grow, it would automatically scale up, and it would scale up in ways that wouldn't increase the latency per request. So as you get more users, you'd have to buy more machines, but the latency per request wouldn't go up. It would scale. So some of the key innovations are a replacement for SQL, a performance safe query language called Pickle, declarative performance consistency trade-offs. One of the big things, instead of have the ACID semantics, is to let you say, well, we'd like these things to happen in 10 seconds or it'll happen in a minute, and then using the director to automatically scale up and scale down. Okay, so good thing I added some slides. All right, so I'll have even more time for questions here. So we think cloud computing is really a big deal. We think this is going to transform the information technology industry. For those of us who build hardware, if instead of selling a server one at a time, you sell a container full of services, that's going to affect the way you design hardware. I think cloud computing will affect hardware the least. For the software industry, anybody can become a software as a service rather than shipping CDs. You'll be shipping it as a service. I think in the next decade, this is going to transform the service industry, the software industry. And kind of remarkably, the technology is there between the software and cloud computing that anybody in the world can build the next great service. It's not a select few with the companies that can make the best. Anybody can do that. All you need is to get popular and then grow as the man needs it. As I said, I think, it's hard to, there must be industries that cloud computing is not going to have any impact on it. It's hard for me to think of what it is. Certainly academics, both at the research enterprise and the education enterprise, it's a great match for cloud computing. It'd be embarrassing if 10 years from now we haven't embraced cloud computing to try and make things more cost effective. From a kind of a research side in systems, it's got this new challenge. Systems that have to shrink down as well as shrink up. And it's got this nice characteristic of shrinking down is it's more shrinking is kind of conservation. It's environmentally friendly. And then the project at Berkeley is taking on a lot of these challenges. We've been working on it for several years. And you can go to our website and see what we're doing or go to Armando's talk. All right. Thanks very much. Okay.
So if there are questions, please raise your hand so I can go and bring the microphone to you.
I need the first question. Great. I'm a bit long-winded. I'll try and keep crisp answers.
One challenge maybe deserves more attention is security. So suppose NATO or Warsaw Pact wants to use cloud computing, which would be natural and advantageous to them. But then it's a kind of paranoid world. You put stuff which is very secretive. Or big pharma uses that.
Yeah.
And if you just, on the other side, suppose I'm Microsoft, you put your stuff, just as storage, you encode the whole thing. I have no idea what it is. Then you take it back. Then, of course, you're safe, but it doesn't buy you that much. So it's important thing that on the cloud you can do certain things with the data, even though it's encoded. So I'd like to hear
Yeah,
your
so what's
thoughts.
the comments on that? Yeah, so I've heard that people of cloud computing companies give keynote addresses in lots of forums, and privacy and security is one of the first questions they always get. So I think, let's just talk about companies. Not surprisingly, the way companies get started in cloud computing is they put things out there to get experience with it. And the more success they have, the more they do. And then some of the interesting things about how could you imagine this ever happening, given seems like a pretty insecure thing. Well, at least in the United States, every major corporation outsources their payroll to this single company. And they've been doing it for at least 15 years. And so nobody does their own payroll systems. Well, payroll is pretty sensitive information. So how do they get away with that? Well, people have been using this company for a while. They haven't leaked this information, and so they just do it. Another example is email. Boy, you know, I don't know what I have that's secret in my house, but boy, my email has a lot of stuff in it, right? So many corporations outsource their email. So why do they, you know, if they were worried about security, why are they doing that? I think they've got some level of comfort now about outsourcing email systems. You know, I don't know if Berkeley, I don't think the University of California, we're not supposed to outsource our email, but you know, governments, cities, corporations have outsourced the email. So there's examples of two very sensitive things that in practice people have felt comfortable doing, even though theoretically could do that. And you know, like I said, it's not like cloud computing users don't brag about their use of cloud computing. But I believe that all these companies that are here, if you ask them, do banks, do pharma people use it, and they do. So like there's laws in the United States about the HIPAA laws about revealing patient things. So some of the simple things they do, if it's these batch processing, is they'll just replace the patient IDs with some some intermediate information that they only know, and then send the data there and bring it back. I think for batch processing, I believe corporations aren't as worried. You know, it's there for a short time. They do the work on it, and they get it. You know, they could destroy it, or they could encrypt it while it's there, and then get rid of it back. They don't seem to be as worried about that. I think you'd be worried about more services. But I think the trade-off is this elasticity here, right? The opportunity without making a giant investment of being able to have 10,000 servers working on something, you know, right now, that's at low cost, is pretty attractive. So I think what's happening is people are all naturally worried about security and privacy, but boy, that's sure cheap, you know, and boy, that's going to be a lot less work. Suppose I want to do a new service. Boy, I could do it there. I talked to the people at Netflix who were converting all of their movies to from one format to another. I think H.264 was where they were headed from MPEG-4. And so what was the reaction of the people there? He says, well, the programmers loved it because they kept, their software wasn't working, right? The deadline was April 1st, and they, you know, well, it doesn't work great, doesn't work great. Well, they finally got it working 4 days before the deadline, right? Went to cloud computing, got it all done, made the deadline. So that elasticity is pretty attractive. And I think it's overcoming, the cost in electricity overcomes the anxiety about security. So I think we're seeing companies do this. And there's examples, it's so cheap, where programmers just take out their credit card and go use it and hope they'll get reimbursed afterwards by their company. So I think people are kind of voting with their feet. And I think when I hear the conversations about security concerns, it's usually from people who haven't tried it. Or they're probably not going to try it. They just don't. They can't imagine how anybody would use it since the obvious security concerns. But although it's not published, my impression is that this is being overcome. The practical advantages are overcoming the kind of obvious security concerns.
You're giving a very enthusiastic picture for everything on the cloud. But the history of the IT industry is made of a sequence of swings of the pendulum back and forth between using centralized resources and decentralizing to users. You know, we've had mainframes, minis and personal computers. Then we had thin clients, smart clients. Then we'd have client-server, web services, and so on. So do you think this is the last swing of the pendulum, or is there any limit, and are we going to go back to more power in the hands and at the location of the user and the programmer?
Yeah, I didn't give you my... we've been saying for a while that we think the extremes of computing are the most interesting. So battery-operated things like this, on one hand, and the cloud on the other is where things are headed. And I mean, who knows in the longest? Who could possibly know what the world's going to look like in 50 years? Who could possibly know? But I think in the next decade or 15 years, doing things for battery-operated devices, the programming environment there, and then the cloud, and I think that's the programming environment. The exciting programming environment of the future is applications are going to be in the cloud and on the client, on the battery-operated client. And depending on your circumstances, like your connectivity or battery power, the applications may shift back and forth. I find that a very exciting future, and I think my advice would be, if you're looking for a research project, that's a pretty interesting research project to work on. It's got these security issues. It's got battery life. What are the opportunities there? What's the cost? What's the battery cost of transmission versus local? So I think that's a very exciting future. There's a bunch of legacy stuff that as a researcher's perspective, I just don't care that much about. But I find that a compelling version of the future. I don't think that's going to go away. I think people are. I mean, the cell phone's is the most successful information technology device of all time. I believe I'm the first one to notice this. Half of the people on the planet have a cell phone. More than half. The majority of people on the planet have a cell phone. Out of 6.7 billion people, there are 4 billion cell phone plans, and probably, if we assume, amazingly, like 10% of people have 2 cell phones. Okay, so if we subtract those out, that's still more than half of the people in the world. And they think it's going to grow to 3/4 of the people in the world. We have never had a technology that's that way. So I think people are voting for portable communication devices. So I can't imagine that one going away. And how are you going to complement that? And I think the cloud. So I think 10 or 15 years, it's going to look like this. Yeah.
So I'm Antonio Cisternino, University of Pisa. So I wonder, what do you think about the following statement? So perhaps the main difference between cloud and grid is that the cloud focuses more about data and their location and processing rather than about computations.
I know Armando has an opinion. Why don't you stand up and... I mean, I don't understand the grid a little bit.
I don't speak for Dave Patterson, but I think the difference between the cloud and grid is Amazon didn't pretend to know what everybody wanted. The x86 has steamrolled everybody. We believe a lot of people would be willing to buy this commodity product, which is a rentable x86 VM. Let's sell that. Right? There's no software infrastructure. There's no tools. There's no batch of this or that. There's no federated policy. It's just here. You use this machine for a while. Knock yourself out. It's a very practical difference. It's the difference that a business person's approach would have made, right? Don't pretend that you know what everybody wants. That's only my opinion.
Yeah, and I think the grid didn't concentrate as much.
I'm not a grid user, but a happy cloud user.
I always thought the grid concentrated more on computation than it did on data, right? And this is what I like about capitalism, right? It's well, there are all these ideas out there. Let's try them, right? And capitalism allows the one that's popular. And I know the people at Sun who did their cloud computing thing. They thought no one would use something where there weren't guarantees. Amazon will make it cheap. There's no guarantees, and it's really popular. And they were stunned. I mean, why would anybody use a cloud or utility if there's no guarantees, right? And there have to be contracts. We have to have, since there's guarantees, we have to have contracts and penalty clauses. You got to sign a contract to use it. No, credit card, no guarantees. So it was another model, and it's caught on.
Hi, thanks for your great talk. Two questions. First one is on cost associativity. So it's true that if you look at on-demand instances at EC2, for example, that this is correct. But on the other hand, immediacy does cost. If you want to allocate, let's say, 1,000 servers at an instant point in time, it does cost you more in an on-demand fashion, where you can compare to a reserved instance. Yeah, you can reserve these.
Yeah, you could also
so there's a difference there.
Yeah. Okay, what's the question?
Yeah, so the question is, I guess that's one important issue to take into account. And also the second issue is that, do you think there's no opportunity maybe for certain providers to deliver volume discounts, which would kind of distort this relation a little bit?
Okay, so I think the first one was what about reserved instances was kind of like renting versus instantaneous. And then the second one was volume discounts, right? So the first one, well, actually we'll get in a lot of arguments with economists in particular about, oh no, this won't work, right? In fact, the review of our paper in Communications of AECM was, I don't care what people are doing in the cloud. It doesn't make any sense. They should change their calc. We know this is the wrong charging algorithm. And when we talk to the cloud providers, you know, a simple to understand cost model has advantages in selling it, right? So I think, you know, this reserve instance where you rent, you know, it may have practical things to do. What's exciting to us as researchers is the scalability, right? Can we create software that can take advantage of that opportunity? Because for me, if you rent stuff, I can more or less guarantee you're going to be wasting power. A lot of the time it's going to be idle and you'll be wasting power. And I don't see how a cloud provider can turn that off because you've rented it, right? That's your responsibility. And so I like it. It's a much more, I don't know, engineering sensible, conservationist-oriented thing that you grow and shrink as you need things, right? That's that one. What was the second one again?
I was going to pose the second one. It's about the green, let's say, argument. So I certainly subscribe to the idea that you can do optimization there with green energy, co-location with energy generation facilities, with data centers. But on the other hand, you're also removing constraints from consumers of using these systems on a very large scale. So do you think there's a certain risk of this system getting a bit overloaded when everyone starts jumping in with very large-scale computing and demands there?
But the job of the cloud computing provider is to provide the illusion of infinite scalability, and they have to manage that. But we've transferred the risk from us to them. So far, in our experience, they've managed that. The other thing you asked about volume discounts. I suspect if you were to go to one of these companies and say, we want 100,000 servers, I bet you don't pay the same that I do. I bet that's there. But I think there's kind of a beauty in their standard charging algorithm that it's easily flexible. And I don't see any evidence of them changing it. They've lowered the costs over time and provide new types of instances. But this simple model has stayed, and it's attractive to us. What I like about it as a researcher, I've always been interested in cost performance. And whenever, as a field, we do performance, and when you bring up cost, people don't trust you. This has cost. I mean, you don't have to argue about it. This is a cost-performance argument. We just wrote a paper about what we did compared to what it would cost on Amazon, and we were able to calculate the difference there, and nobody's going to argue about that. So I like that too. All right, I told you I was long-winded.
Who else has questions?
There's still more time.
Hi, my name is Rodrigo Serra from Unicamp. We saw earlier today e-science in the clouds, and then we saw education in the clouds. And I have the gut feeling that in the future we might see desktop in the clouds, like people using the clouds as a major synchronization media for multiple gadgets, and as a way to preserve their data and a way to save energy. Do you think that cloud infrastructure today would have to change what it's doing if such demand comes?
I think, like I said, I love that we're in a fast-moving field. I'm really glad I'm not in history, right? Where I don't know what's the new innovative thing you teach, about something happened 2,000 years ago, but I'm sure there's something. But, wow, we're in a fast-moving field, and it's really exciting. People are making different bets. There are people who are building clouds that have thousands of GPUs on them, right? And so that their idea is they're going to do gaming all in the cloud, and your device is going to have very little in it, right? And that's the way to do games, right? I don't know, that doesn't strike me as a good idea, but people are trying this right now. So how fast is wireless communication going to improve? What about how are people going to build cell phone towers? There was an article this week about AT&T having, instead of a cell phone tower, you have your own little tower that you put in your own home. And so there's all kinds of interesting things that are going on. The one, I think, negative is probably internet bandwidth. The one, as a person who's a kind of a cheerleader for new technology, a cautionary tale would be internet bandwidth. Internet bandwidth, at least in the United States, isn't so much technology-driven as monopoly-driven or standards-driven or something like that. Is internet bandwidth going to get a lot cheaper in the next few years, or is internet bandwidth go up a lot in the next few years for the same price? Boy, that's harder to figure out. One of the reasons is the cost of the switches in the data centers. The multi-million-dollar Cisco switches set some kind of limit on how cheap that can be. Maybe we'll need innovative new switches, much cheaper switches to bring the cost down. So I think the internet bandwidth one is sticky, but boy, the wireless stuff and what people are doing in hardware and energy efficiency, it's hard to, I'd be afraid to say something that can't be done. Now, I think Microsoft already offers all of its desktop apps that many of us use. There's a cloud version of all of that today. So it's easy to it's easy to imagine anything being anywhere. On the other hand, in Berkeley, there's places I can't get wireless access in Berkeley. So I would particularly like whatever my wireless gadget is to be able to do stuff locally without being disconnected. So I think that's why I think this kind of shuffling back and forth between the cloud and the device will be a pretty exciting area.
And we have one more question.
At the rate that I answer.
It's kind of a follow-up question to your points around bandwidth, and that's do you know? Have you looked into a theoretical maximum for storage? How someone goes about storing in the cloud, either using a bandwidth upload ingress methodology or through just a FedEx sort of ingress bulk intake?
Yeah, I don't think we've calculated that, but disk capacity is continuing to grow. FedEx doesn't change. We could ship a lot of disks anywhere in the world quickly, within a day. So if I was doing, that's the way I would do bulk transfer there. It's hard for me to see some practical limit. I think disk is still improving almost by, the areal density of disks, I think, is still improving by almost Moore's law. And you can calculate how much it would to ship a box of a certain size would do that. But I think that's probably the way I would calculate. If I was going to say what makes sense to do, you could certainly ship. Well, you can get multi-terabyte disks today. So could you ship a petabyte economically? I wouldn't be surprised, right? Or a big fraction of a petabyte if you worked it out. That's plausibly you could do. And then you'd grow by kind of areal density improvements from that point. So I don't know if that's a theoretical argument. There's a practical argument of something. That's why I would do it practically.
Okay, thank you very much. Please join me to thank him.
All right.